Hello students, so in our today's topic or today's video, we would be starting a new chapter of electrostatics. And as mentioned, today we would be talking about capacitors, right? So let me first get started with the flow of topics for this chapter because obviously it would be a series of at least 4 to 5 videos. So let me help you with the flow of topics, and then obviously we will get going with the real subject matter, right? So the flow of topics in capacitors would be today we would basically try to understand the concepts piece of it. So we would understand what do we mean by a capacitor, why is a capacitor needed in an electric circuit at all, and things of that nature. So today it would be predominantly an introduction, okay? And then we would move on to evolution of capacitors, right? The evolution part. So after establishing the concept, we would start. So just like we studied in your Gauss law or electric field due to a continuous charge distribution, we started with, say a point charge, and then we saw for different geometry. So similarly, we would see that why conceptually there is a spherical capacitor, and then why did the world moved from spherical capacitor to a spherical cell capacitor to a parallel plate capacitor to a cylindrical capacitor. Okay, so we would see all those evolutions, after concepts. Third part, and we would then be predominantly concentrating on the parallel plate capacitor, and we would see force on a plate due to the other, right? And then we would see after we are done with one single capacitor, we would see grouping of capacitor, and in grouping of capacitor, we would see the series and parallel grouping, just like we saw in your resistances. We would see different geometry of electric circuits, and we would see how do we resolve them. And we will end this chapter by discussing about charging and discharging of capacitors. So this would be the flow of topic, concepts, evolution of capacitors, force on one plate due to other, grouping of capacitors, charging and discharging. Yes, one part I missed out. So here, before going into group, between grouping and charging and discharging of capacitor, we will also see effect of dielectric. Okay, effect of dielectric. So this would be our flow of topics for capacitors. So let's get started, students, with the starting or the concepts. So let us understand that when we are talking about a capacitor, so what are we actually talking about? So as the name suggests, we are talking about capacity of something. But what is that something? So are we talking about the capacity of you and I understanding physics? Are we talking about our capacity of earning or what, right? So fundamentally the answer is, when we are talking about capacitor is an electrical device that stores charge, right, or that is used to store energy in the form of charge, and it provides that energy to the electrical circuit in a burst when it is needed. So the basic definition of a capacitor is, it's an electrical device. It's an electrical device which does what? First thing is, it stores electrical energy, electrical energy in the form of charge, in the form of charge. And second is, provides the stored charge or electrical energy in a burst. This is important, in a burst to the required electrical circuit, right? So I repeat, so the two important properties or two important property of a capacitor is A, it stores electrical energy in the form of charge, and second, it provides the stored charge to the electrical circuit in a burst. So to understand it, let us we would go into an analogy to understand. Probably you would have seen something that looks like a cylindrical, a white color cylinder connected to your ceiling fan or a cooler or at times to your motors, right? So that device is, and many times you would have heard from the electricians and maybe from the electrical mechanic, they call that as condenser. So that condenser which they are calling, that is nothing but a capacitor. And the reason why that is needed is, right, so to start something we need a burst or a push. So just like in your Newton's law of motion, you had studied that to break the inertia you need obviously a stronger push or a stronger force, and then to continue the motion you don't really need that much of a force or that much of an energy to be applied, right? So similarly, there are many electrical devices. To start them we need a burst of electrical energy, we need a lot of electric current to be sent into the electrical circuit in a burst so that it will get started. And once it is started, then your regular flow of electric circuit or the regular flow of electric current in electrical circuit can take care of its functioning. So for example, we would have seen that in home sometimes when and these days that is not, it is not that common, but when we were kids it was more common. Let's say if a fan is you have switched on the fan, but the fan is not rotating. Sometimes you would have seen that we take a stick, we just rotate it, leave it, and then it continues rotating. So remember students that to overcome this initial static friction for devices like a fan, devices like a motor, devices like a cooler, we need a burst of electrical energy, or we need a burst of electricity. So that is why capacitors are connected in the electrical circuits to store energy and to produce or to provide electrical energy into the circuit so that the appliances can overcome the initial static friction. Now, to understand this little better, let me give you an analogy, and that would help you understand how does a capacitor function and why do we say that we are storing electrical energy in the form of charge. So once we are saying about charge, then we are talking about energy. So why are we using these terms interchangeably, and what is the relationship? So let us take an analogy, right? So say suppose there's a fort, right? And this suppose the entry gate of the fort, okay? And here the soldiers of this fort, suppose this height is some h, okay? This height is some h. Now the soldiers have created a cliff here, and they are putting a lot of stones here so that when enemy attacks them, suppose this is your enemy soldiers, so when enemy soldiers are attacking them, they want to throw these in a burst so that they can kill the enemy. I repeat, the functioning is, say this is the entry gate of a fort, okay, and the soldiers inside the fort, when there is no war, they have picked up stones of big size. They would have used a ladder, or they would have used some arrangement to pull all these stones onto the cliff, and they would have stored these stones on the cliff, so that when enemy attack the fort, they can throw it in a burst onto the enemy soldier, and they can kill them. Remember, this is very much analogous to what we do in a capacitor. So in a capacitor, so here what we have done, we have we have with every single stone. So suppose initially there was no stone. If initially there is no stone, then what is my capacity of attacking the enemy? It would have been zero, right? So I don't have any stone here, and assume that we are talking about only stone as a weapon to kill enemy. So initially, when there was no stone, the soldiers inside the fort had no capacity to attack the enemy. Now, when one stone is kept here, suppose its mass is m1, we know that m1g8. So this much of potential energy is stored, right? And this can be used to attack the enemy, if there is an enemy attacks on the fort, right? So similarly, as I keep putting more and more stones here, right? As I keep putting more and more stones here, or when the mass is increasing, obviously your potential to attack the enemy, that is also increasing. And in the entire arrangement, your capacity to attack the enemy, this has increased. So similarly, in an electric circuit, a capacitor is a device, right? Where here, see, I kept adding mass. Initially there was no mass, then I added m1, then I added m2, then I added m3, then I added m4. So as and when I kept on adding mass, the potential energy, or the gravitational potential energy, increased. Similarly, in a capacitor, so when we start charging a capacitor, as we start storing charge in a capacitor, so we keep storing charge, its potential increases. Keep storing charge, its potential increases, and obviously its energy of that system increases. When it is needed to the external system, it is given in one burst, take all the energy, do whatever you want to do, finish. So that is what is the basic use of capacitor, and we would see some more analogy. So if you see here, what did we do? The potential of the ground, I can take it as zero, right? Because we know potential is always a point function, right? It depends between your initial point and final point, and how you have made the movement, right? So it is just a point function. So so similarly, in your capacitor also, we would see that we would bring charge. So here what did we do? We brought mass from zero potential to the required place, so that the potential of the system increased, and we stored energy in the system, and we used it when it was needed. We would see that we would do exactly the same thing in case of a capacitor. In a capacitor, we would store charge. So in the process of storing charge in the capacitor, we eventually have stored electrical energy in the form of charge, and that electrical energy would be given to the electrical circuit as and when needed. So that is the basic functioning, or the basic principle of capacitor. So I repeat, any particular arrangement, or any device which has a capacity to store a lot of charge, or capacity to hold a good amount of charge for a longer duration, is a good capacitor. And obviously it should be able to dissipate that energy, or dissipate that charge to the external electrical circuit when needed. That becomes a good capacitor, right? So with this concept, let us understand that which kind of materials or substances are basically used in a capacitor. Okay. So now we said one, it should be able to hold or store charge, and second is it should be able to provide stored charge or energy in a single burst to the circuit. So they are the two things. So now let us let us contrast between a conductor and an insulator, right? So intentionally, I am not discussing too much about semiconductors or dielectric here because their property would be somewhere between the insulators and conductors and insulators. So if we contrast these two, we would understand, that where, to store charge, to which kind of material we would be swinging towards, right? So let us think of an insulator. So say, obviously this marker or this pen is an insulator. Now, suppose if I try to charge this end of this insulator, right? So if I give some charge dq to it, right, it would that charge would be located in the area where I am providing that charge, because we know that it's an insulator, and obviously in an insulator the charge dq which I would have given to this end, it will not propagate throughout the body. It is not, because that is the property of an insulator, and that charge would just get accumulated in the same place where I'm charging. Now if charge starts accumulating here, so obviously the potential of this would increase, right? So just remember the analogy. You in our enemy and foot analogy, I kept adding mass, and the potential to attack or kill the enemy increased. So similarly, I kept adding charge, and that is stored in one place, then obviously potential of this end would increase, and this insulator would very quickly attain equal potential to the device which I'm using it to charge. So once potential of both the things become same, obviously the charging would stop. So that is why though insulators though insulators can store charge, obviously it would not be able to store a huge amount of charge. Also when it is required to give to the external circuit, right? So if I'm connecting a conductor, it would give, but as the charge is very small, so it would not make any help to me, right? So that is why fundamentally when we have an insulator, that does not become a good candidate to be used in an electrical capacitor. Now let us think about conductors. Okay, now assume that this would have been an say a metallic piece, right? So assume that it's a metallic piece of cylinder. Okay, so how can I charge it? To charge it, I may connect it to some external electrical circuit, and that is why when I am connecting it to external electrical circuit, so obviously if I'm giving some charge dq here, we know that it's a conductor, and obviously every conductor is having an equipotential surface, right? So which means the potential of everything on this surface should be same, and the charge which I'm giving here, it would immediately transmit that charge to the nearby atoms, right? Similarly, the next atom would transmit to the next atom, next one would transmit it to next one, so that assuming that it's a uniform conductor, the charge distribution would also be uniform. If the conductor is not uniform, obviously charge distribution will not be uniform, but but the total charge which I'm giving here, that would be spread across the surface. So obviously that means that I can give more charge to it before the potential of this one becomes equal to the potential of the potential of the agent which is charging it, and obviously that is the reason why if I'm using a conductor to store charge, I can store more amount of charge, and that charge can be given to an electric circuit in a burst. Now let us pause here for a moment and think a little deeper, right? So assume that this is a conductor and this is charged. The moment if I connect it to a circuit, right, so obviously charge would flow from one end to another end, assuming that it's a closed circuit. And if charge is flowing, but what do I want? Do I want a flow of charge, or do I want charge to be stored? The answer is, when I'm talking about capacitor, I want to store charge so that it would be given when needed. So it's like this, right? So if I'm earning money and at the same time I'm spending money, my saving is zero, right? But what I want to save money, save money, save money, save money, save money. When there's an issue, or when I get into a financial crisis, use all my money. That is what I want to do. So that is why we use conductors, but we isolate the conductor in such a way that charge would get stored and it would not flow across. It would not flow across, because if charge is flown, then it's over, right? So you don't have any charge stored at all. Okay, so that is why when you read about capacitors, many times you would see people say capacitor or conductor or condenser interchangeably. So do not get confused that, hey, I studied about parallel plate capacitor, but in exam I'm getting a parallel plate conductor. So what this is, right? Or I studied about a spherical capacitor, now I'm getting a spherical conductor. So this is completely different. So don't get confused on it, okay? So we understood this, right? And another interesting thing, if you see, a good capacitor, a good capacitor, another property is, even if you give it a lot of charge, its potential does not increase too much. And why that's a required property? Again, in the same example. So this is the conductor which I want to charge. If I want to charge this conductor and this is my charging agent, I'm connecting them. So we know that charge would flow from your charging agent to this conductor, as long as this one's potential and charging agent's potential have not become same. The moment their potentials become same, obviously your charging would stop. So a good conductor would always have the property that A, it can store a lot of charge, and in spite of we giving a lot of charge, its potential does not increase too much. I repeat, a good capacitor's property would be it can store more amount of charge, and in spite of giving more charge, its potential difference or its potential will not rise, a lot. Just imagine one thing. Let us go back to our same analogy. Okay. So suppose here if the potential becomes too high, which means if it becomes too heavy, then what will happen? It will break that cliff, right? And all the stone will fall. So before the enemy comes, the cliff will get broken and the people themselves will die, right? So an ideal capacitor would be, you can put as many stones as you want, but somehow it would manage that their potential would not increase too much, so that you can keep adding a lot of stones and the cliff is not broken, and all the stones can be thrown to the enemy when the enemy attacks the fort. So that is how normally a capacitor works, right? So if we have understood this theory, so let us go a little bit more towards the practical definitions of a capacitor. That that so we went to the first definition, that a capacitor is an electrical device that stores electrical energy in the form of capacitor. sorry, in the form of charge, and it provides it to an external circuit in a burst as and when needed. So that is why we need capacitors in an electrical circuit. Now, from a definition perspective, from a definition perspective, the way a capacitor is defined is, so we know that okay, so let us just see one more analogy, and then we will go to the rest of the things, right? So for example, I take a conductor of any shape, okay, and somehow if I have given it a charge q, okay, if I've given it a charge q, it will have a potential v. Now, okay, even before this, so let us just see how can I give it some charge q, right? So initially we know that it will be charge neutral, right? So the number of positive charge would be number of equal to the number of electrons. So net charge on this conductor would be zero. So net charge will be zero. Now suppose, just like we did in our analogy example, right? So we started pulling stones from zero potential to the required point, right? So zero potential to required point. In an electrostatic field, in an electrostatic field, which place is considered to be at zero potential? The answer is obviously infinite or earth. So we know that if we are earthing something in an electrical circuit, that is considered to be at zero potential, or something that is at an infinite distance, we consider that to be at zero potential. Why? In electrostatics, we have studied that potential equals to 1 by 4 pi epsilon naught, right? Q by R, kq by R. So it is inversely proportional to R. So obviously, when limit R will tend to infinite, what would be the value of this? This would be zero, right? So that is why potential of infinite is predominant, is considered to be zero in electrostatics. So now, if I want to charge this conductor, then what would I do? Suppose at time t equals to 0, I would try to get a charge dq from infinite to here, right? So suppose this is at infinite distance. From infinity, I would get the first burst of charge dq. So we know that charge is quantized, so we can get charge in bursts. Okay, so I got charge dq from infinite to here. Now, this was completely electrically neutral. If this is completely electrically neutral, is there anything to obstruct this? Obviously, no. If there is nothing to obstruct it, I can easily, take this charge and put it here, right? So at t equals to 0, your charge was 0, your potential was also 0, right? After I have brought the first dq, when I would bring the second dq, okay? So suppose one dq is already here. When I will try to bring the second dq, so when this second dq is coming, right, and obviously I would assume them to be of the same sign. If this is positive charge, I'm bringing positive charge only. So we know from electrostatics that like charges repel and unlike charges attract each other. So when I am trying to bring this charge in this direction, obviously this charge would provide a repulsive force Fe in this direction. If there's a repulsive force Fe, and I am bringing it from infinite to suppose this point, obviously I would do some work on this. So your and how much of work would I do? I must apply a force. So I must apply a force F in this direction, F external, such that my F external must be equal to my electric field, right? Or it should be slightly more than the electric field. In physics, will for calculation purpose, we'll take F external equals to Fe. Now, when this is there, so obviously I can say that my potential energy, potential energy is nothing but either work done by this force or negative of work done against the internal force, whatever you want to say. I repeat, in physics, we have studied many times that potential energy is nothing but work done by the external force, or it is negative of the work done against the internal force of the your what you say that provides the field. So that is why when I would try to bring the second dq, right, so this guy would provide an electric field, so my electric field will be how much? K dq by r square, right? Assuming the distance was r, and obviously as the distance is changing, I need to at any point of time I need to fix up the distance, and then I will do the dot product with your displacement to find the the total work done. So that is how I would do, right? So that is why when we are bringing more and more and more charge, obviously it will keep pushing it more and more. And obviously when you have charge equals to q, when you have charge equal to q, your potential will be how much? K q by r. So with a so due to this kq by r, as you have charge q here, it will push it. Now, obviously, when your charge dq is getting a repulsion, you need to do work against the electric field, and obviously that work done which you are doing, that would get stored in the form of electrical energy. Just like here, your earth is pulling it down, right? Earth's gravitational field is pulling it down. You are doing work against the earth's gravitational field. So that is why when you are pulling this mass m to this height h, you are storing a potential energy mgh here, right? If you want to calculate the potential, you have to divide the mass. So similarly here, when we are calculating the potential, it will be energy divided by charge. So that is why when we bring charge from infinity to this point, obviously your potential increases, and obviously the work done in that entire scenario gets stored as the electrical energy here, okay, and that gets given to the electrical circuit in a burst as and when needed. Okay, so I think this is a lot of theory. So now let us move a little bit towards the evolution of capacitor. Okay, so but the reason why we discuss this is, once we understand this, the rest of the journey will be very easy. Okay, so the definition says that capacitor is created by placing two conductors of any shape. So suppose this is one plate, this is another plate. Okay, so when two plates are separated by a small distance d, okay, one is given a charge plus q, another is given the charge minus q, right? So this arrangement is called as a capacitor. Okay, I repeat that a capacitor is formed by two plates separated by a small distance, and by giving a charge plus q and to one and minus q to other. And obviously why we are giving charges to them, so that a potential difference v would get created between them. Okay, and from a definition perspective, charge on the capacitor is always taken as charge on the positive place of the capacitor, and we do not say that here we have charge plus q, here we have minus q, so net charge is zero. So we don't really talk about that. We say charge on the capacitor as charge on the positive plate. Okay, and it is noticed that your charge q is directly proportional to the potential difference. Okay, so and from here we get your q equals to cv. Okay, and this proportionality constant c is called the capacitance of the capacitor, okay, capacitor, or can I say that the capacitance C equals to Q by V or delta V, whatever you want to say, okay? Q equals to C equals to Q by V. So this is how your capacitance of a capacitor is defined, right? So let us go into the units and dimensions of the capacitor. So students, capacitance also, the way we will define is capacitance C, okay, the SI unit. The SI unit, or the capacitance is defined as the ability to hold charge of the conductor such that for the amount of charge that is required to increase the potential difference by one, right? So if my denominator delta V equals to one, then my C will be equals to Q, right? So that is why we say capacitance of a capacitor is the amount of charge that is to be stored in the capacitor to increase the potential difference by 1 volt, or 1 unit. Okay, so volt we will not use here because we have not yet gone to any system of units. So we'll say capacitance of a capacitor is defined as the amount of charge required to be stored to increase the potential difference by 1 unit. And if you see here, what we have studied theoretically, that is coming here also, that a good capacitor should be able to store a lot of charge. Q is coming in the numerator, right? And even if, and when we are storing charge, its potential should not rise, very quickly. See, V is coming in the denominator. So if V is small, obviously the value of the fraction is more. If Q is more, value of the fraction is more, right? So obviously this is in line with what we have studied theoretically for capacitance. Okay. So after this, now let us move into the units of it, or the unit of it in your what do you say, SI unit, and the dimension. Okay, so your capacitance is always a scalar quantity. Why? Capacitance, we are saying charge Q by V, right? So we know charge Q, this is nothing but a scalar, and V we know this is nothing but your E dot di, right? Or I can say, suppose just for understanding sake, I can say E dot R, where E is nothing but electric field and R is nothing but your your gradient, right? So obviously dot product of two vectors is a scalar. So we know from our concepts of scalars and vectors, a scalar by a scalar. So obviously the division or the output of this will also be a scalar. Okay, so a very simple question, if you get, is capacitor or capacitance a scalar or a vector? It's a scalar, and this is why, or this is a small way of proving it, though you may not get a question to prove it, but just for understanding purpose, that capacitance is a scalar. Okay, now let us see about the units and dimensions. Okay, so the SI unit of capacitance is called 1 farad, is called farad. Okay, okay, so and as we know that, even if we will always start it with a small letter F, right? And if we denote by symbol, it will be 1F. Now C equals to Q by V. For C to be 1 farad, what should be the value of Q? It should be 1 coulomb upon 1 volt, right? So it will be 1 coulomb upon 1 volt, right? So then you will get your capacitance equal to 1 farad. But remember, students, that the unit 1 farad is a very huge, it's a very huge unit of capacitance. So any capacitor which you see in the market, which you use in electrical circuits, you would see in terms of microfarad, which means your 10 to the power minus 6 farad. Okay, why and how we would see in next few derivations, and we would be able to realize that how big 1 farad is, or how huge a unit 1 farad is. Okay, so let us keep moving. So let us get into the evolution of different type of capacitors. Okay, so here let us start with a spherical conductor or spherical capacitor. Okay, so just like we have studied in your electric field also, we started with a point charge, then we started with a spherical conductor, then we went into your, what you say, charge distributed in a straight line, charge in a sheet, right? So similarly, here also we'll see what are the different geometries of capacitors and all those things, right? So let us keep moving. So spherical conductor or spherical capacitor. So what are we doing? We are saying that suppose we have a spherical conductor of, suppose, radius r. Okay, so we have a spherical capacitor of radius r, and if I have given it a charge q, obviously, and assume that it's a positive charge, you can take negative also, not an issue. So obviously that positive charge q would have got spread on its surface, right? And as it's a uniform capacitor, your charge distribution will also be uniform. So whether or not charge distribution is uniform, we know that charge will have got distributed on the surface of the capacitor. Now we want to find out what is the capacitance of this spherical capacitor. Okay, and after we derive it, we would see something very interesting right here. Okay, so we know capacitance C is nothing but Q by V, right? So charge is given as Q. If I can find out the potential on the surface, I can find out capacitance of this spherical conductor, right? So obviously, when we have created this spherical capacitor, right? So we know that, let us try to find out what is the value of V, right? So how do we give charge q to this, right? So what we would have done, as we were just discussing before some time, I showed a irregular shape body like this, and I said initially there was no charge on this, right? At t equals to 0, charge was 0. Okay, and obviously your potential was 0, right? From infinite, I brought the first charge dq, right? So when I'm bringing the first charge dq, still there will be no, potential will be 0 because no charge is there to obstruct it. Assume that after some time there is a charge q here. Okay, if there's a charge q here now, okay, and I am trying to bring a charge, next burst of charge dq, so obviously because of this charge q, there will be an electrical force here, electric force, right? And if I take force per unit charge, I can also say that there is an electric field. The reason why I'm taking electric field is I want to find out potential. We know potential is nothing but potential energy upon unit charge. So that is why what I'm doing, I'm taking force per unit charge, and I integrate it with your displacement. Okay, so that's why I'm taking E. Okay, or we know your E equals to dV by dr. We are fundamentally trying to use it. Okay, so that is the reason. why we are doing it like this. Now, there would be an electric field E in that direction, okay? And my displacement is in this direction, right? So if I at a distance, suppose r from here, okay, and if I know the potential dr, then I know that I can say electric field due to this charge q at this point e is nothing but 1 by 4 pi epsilon naught q q by r squared into uh, kq by r squared. Yeah, this will be my electric field. If this is my electric field, then what would be the work done? Work done would be this much dot product, the displacement vector dr, and when I would integrate it from infinite to this point, right? So E dot dr integration, we know from electrostatics that V equals to 1 by 4 pi epsilon naught q by r would q by r is what I will get, right? So now, if my potential V equals to 1 by 4 pi epsilon naught r, which we know from our electrostatics understanding, then obviously, what would be my capacitance? Capacitance C would be Q by V. In place of V, let us just substitute this value Q by Q by 4 pi epsilon naught r. So obviously Q will get cancelled. This will go to the numerator. So C will be nothing but 4 pi epsilon naught into radius of this spherical conductor. Okay. So here if you see one interesting thing, capacitance C equals to 4 pi epsilon naught r. Okay, so if you see here, capacitance though is equals to charge per unit, potential difference, right? But it neither depends on charge nor on potential difference, because capacitance itself is a proportionality constant, and when you increase q, v would increase automatically, and they would kind of manage each other. Remember, that's why capacitance C depends on just two things: a, dimension of the capacitor. So if you see, radius r is important here, and b, the medium epsilon naught. Okay, so here we have assumed that we have only air inside this conductor, or maybe or sorry, outside this conductor we have only air, right? So in air medium, C was 4 pi epsilon naught r. Suppose I would dip this entire capacitor in water. Okay, if I would dip this in water, then the equation will change to C equals to 4 pi epsilon r, where E is nothing but epsilon naught into your dielectric constant K. Okay, so that's why remember, whenever we talk about a capacitor, the capacitance of a capacitor depends only on two things: A, on the dimension, and B, on the medium. Okay, and what is the importance of medium, we will see in an upcoming class. But remember, whenever a capacitor is created, once it is created, it's obviously its dimension is fixed. Okay, so that is why its capacitance is also fixed. So capacitance depends only on two things: A, dimensions of the capacitor, and B, it depends on the medium. Okay, okay. So if you see here, C equals to 4 pi epsilon naught r, and and this concludes that capacitance depends on the radius or the dimension, and it depends on the medium, or the permittivity. Okay, so that is the thing. Now, if we want to slightly change it, so we are saying that capacitance C equals to 4 pi epsilon naught I, right? Can I say it like this, that C equals to 4 pi R into R, let epsilon naught be here, and I am multiplying one R in numerator and denominator, right? So nothing changes. So can I say C equals to 4 pi R squared epsilon naught by R? So can I say C equals to, what is 4 pi R squared? That is nothing but area of this sphere, right? So area epsilon naught by R, okay? And R is nothing but the the distance between center and the radius. Obviously, it's the radius, okay? So if you see, once we move into your parallel plate capacitors and all, we would see that that is why capacitance depends on, your area of the plate which you are taking, the distance between them, and the medium. So we will see in parallel plate capacitors that C equals to epsilon naught A by difference D, and these all and a lot of concepts we will see in the next class, where there would be a lot of, mathematical derivations, and we would see why the world went from your spherical capacitor to the next, kind of capacitors. One hint which we would start up with, if you see here, C is directly proportional to R. Okay, so I give you a hint. You can try in home that how much big a spherical conductor I would need if I want to create a capacitor of 1 farad. I repeat, just try it out in home, and we'll start our next chapter with this, that how big a capacitor would I need if I were to create a capacitor with capacitance 1 farad in the next class, and we'll see a lot of derivations. Thank you, students. Meet you in the next class.